What is statics and what is static equilibrium? Statics is a branch of mechanics focusing on object at rest or moving at constant velocity, or defined as equilibrium, while static equilibrium occurs when the sum of all forces and torque on an object is zero, resulting in no acceleration or rotation. Static equilibrium applies in two conditions. First condition of equilibrium, when all of the forces acting on object are equal and the object's motion remain unchanged. This known as transitional equilibrium. The forces to the left and right add up to the same amount. The total forces acting upward and downward are equal. So the vector of sum all of the forces is zero overall. Sum of the factor is equal to zero where no linear acceleration. On the on the other hand, when all of the torques acting on an object completely cancel each other out, rotational equilibrium is reached. This is the second condition of equilibrium. According to the principle of moments, the sum of the clockwise and counterclockwise torques about a pivot point must be equal for an object to be in rotational equilibrium. This guarantees that the object doesn't start to rotate and stays balanced. The moment of force is also known as torque, where sum of the moment is equal to 0 Newton. It will show there is no angular acceleration. There are three types of static equilibrium. Firstly is stable equilibrium. When an object is displaced slightly, it tends to return to its original equilibrium position and it experiences a net force or torque in a direction opposite to the direction of displacement. Simply said, object return to the original position after displacement, where potential energy required at minimum. Secondly, stable equilibrium. The object moved away from the original position after displacement, where the potential energy is maximum. When an object is displaced slightly, it moves away from its early position and it also experiences a net force or torque in the same direction as the displacement from equilibrium. It's also defined as unstable equilibrium. And the third one is neutral equilibrium. When an object is displaced, either it's returned or moves away, but stays in the new position. At this position, the potential energy is constant. For neutral equilibrium to occur, the center of gravity must be positioned directly above or aligned with the base of support during displacement. Understanding neutral equilibrium is essential engineering and design to ensure that structures and objects maintain stability under various conditions. Simply said, object stays in a new position after displacement occurs. This means potential energy are constant.
Moving on to four real-life examples of static equilibrium. First, a hanging plant pot suspended by either a single cord or multiple cords. In a single vertical cord, the outward tension force must equal the downward weight of the pot and act along the same vertical line, so the force cancel each other out, keeping the pot balanced. With multiple cords, the vertical components of tension share the pot's weight evenly, while the horizontal components pull in opposite directions and cancel out. Since both vertical and horizontal force are balanced, the pot stays still, meaning it is in static equilibrium. Second, the seesaw, when two individuals of equal weight sit at equal distance from the center point, they apply an equal and opposite torque, so the net torque is zero and the seesaw stay balanced. If one person is heavier, they must sit closer to the center to reduce their torque, while the lighter person sits farther away to increase theirs. This rebalancing brings the system back into static equilibrium.
Apart from hanging plant pot and seesaw, three examples of static equilibrium can be seen in our daily life. The first one is stable equilibrium. If the marble at the bottom of a bowl is slightly nudged, the marble will roll back to the center of the bowl. The second is unstable equilibrium. If the ball at the top of hill is slightly nudged, the ball will roll down the hill and stay on the bottom of hill. The last one, which is the neutral equilibrium. If the book on the table is slightly slide, it will stay in its new position. No net force or torque remain after the action of sliding the book. Three cases of these examples achieve the static equilibrium in the same way. They balance the object's downward weight with the outward lower force from the surface they contact with. The last real life example is a ladder leaning against a wall. The ladder stays still and static by achieving both components of static equilibrium, which are translational equilibrium and rotational equilibrium. The translational equilibrium can be further divided into vertical component and horizontal component. For the vertical component, the downward weight of ladder at its center is balanced by two outward force, which are normal force from the floor and frictional force of the wall. Therefore, the net vertical force is zero. For the horizontal component, the normal force from the wall pushes against the ladder and causes the ladder to slide away from the wall. This force is balanced by an opposite force, which is the frictional force at the floor. With this, the net horizontal force is zero. Moving to rotational equilibrium, the weight of the wall contributes to anti-clockwise torque. This is balanced by the clockwise torque of normal force from the wall. Therefore, the net torque is zero. With this, the ladder achieves static equilibrium.
The phenomenon of static equilibrium can be seen through the balancing of a seesaw by two individuals of different masses, as can be seen in this problem. This problem involves two unknowns, which are the distance of the second child from the selected pivot point on the seesaw, R2, and the upward supporting force of the seesaw, Ft. To calculate the unknowns, a free body diagram can firstly be drawn. This can be followed by finding R2 by applying the second condition of equilibrium, which states that the sum of all torques acting on the system is equal to zero. The first child exerts a positive torque as it causes an anti-clockwise rotation, whereas the second child exerts a negative torque as it causes a clockwise rotation. Meanwhile, Fp exerts zero torque as it acts directly above the selected pivot point and hence has zero distance from the selected pivot point. Subsequently, R2 equals to 1.30 meters can be obtained as shown in the calculation steps. This indicates that the second child who is heavier must sit at a shorter distance of 1.30 meters from the pivot point of the seesaw to balance the seesaw. After finding R2, the value of Ft can be determined by applying the first condition of equilibrium, which states that the sum of all forces acting on the system must be equal to zero. All forces involved in this system are vertical. Both the first child and the second child exert downward negative forces, whereas Ft is an upward positive force. Subsequently, Fp equals to 568 newtons can be obtained, which indicates that the supporting force exerted by the seesaw is 568 newtons in an upward direction.
Greetings, my name is Tam. Together with me, we'll look into the second problem, which is about a climber resting on a slope inclined at 44 degrees. He has a mass of 48 kilograms and carries a 25 kilogram backpack. The slope gives a 5 Newton frictional force opposing his motion. Now, the climber climbs, the rope holding him has only 10 newtons of tension, but is that even enough to hold him still? We are going to check this using the concept of static equilibrium. Alright, now let us move on to the solution. First, we'll draw a force diagram, and there will be three key downward forces. The weight of the climber, that's 78 kilograms times gravity, which is 78 times 9.81. The weight of the backpack, which is 25 times 9.81, and 5 Newton frictional force acting up the slope. We then split all these forces into components along with the slope, which is the x-axis, and a perpendicular to the slope, y-axis. This is important because the rope tension is pulling at an angle of 44 degrees, so its force has x and y components. Now we apply Newton's first law. Since the climber is at rest, the net force in both directions must be zero. That gives us two equations. In the x direction, the tension component minus friction must balance out the pulling force of the slope. In the y direction, the vertical component of tension must balance out the combined weight of the climber and the back. Solving this, we get the tension x component is around 3.6 newtons, and the y component is a massive 1013.9 newtons. Using Pythagoras' theorem, the total tension force turned out to be approximately 1013.91 newtons, almost straight upward at 89.8 degrees from the horizontal. So to answer the original question, no, the climber statement is false. A rope with only 10 newtons of tension wouldn't even come close to balancing the forces. To stay still, the rope need to exert a force of over 1000 newtons of force upward. That's the real tension required for static equilibrium.
My name is Davy, matrix number 23005923. I'll be talking about the real-world application 1 regarding bridge. So there are dead loads, live loads, dynamic loads, and thermal loads involved in these applications. First kind of bridge, beam bridge. How does it maintain the stability? First, vertical force. The sum of the downward force must equal to the sum of the outward force, which is a normal force at the supports on the bridge. Horizontal force is not significant in this case because the wind couldn't really swing the bridge. And moment balance, or known as rotational force, must be summed to zero to prevent rotations. And second type of bridge is suspension bridge. All vertical forces are transferred upward via the hangers to the main cables and then to the towers and anchorages. This force is balanced by the reaction force from the ground at the bridge base and also the tension forces in the cable and anchor blocks. While for the horizontal force, the tension in the main cables will create horizontal forces that are balanced by the anchorages at the end of each of the bridge.
Hi Dr. Vijay, my name is Ada Liu and today I'll be explaining how static equilibrium can be applied to IV drip stents in hospitals. So IV stents are designed to hold fluid back safely and steadily to allow patients to receive medication or hydration over time. So for the stent to remain upright without tipping, it must be in static equilibrium. This means all the forces acting on the IV stent must be in balance. Vertically, there are two downward forces acting on the IV stents, which are the weight of the fluid bag and the stent itself. So the downward forces are balanced by the upward forces, which include the tension in the hook and the normal force from the floor. So when the total upward force equals to the downward force, the stent will be able to remain static. However, in real life, there may be small horizontal forces, such as someone brushing past the stent. This may occur, but these are usually balanced by the friction between the stent's base and the floor, which helps prevent it from sliding or tipping over. So this balance is crucial for safety, hygiene, and ensuring that the IV fluid flows properly.
My name is Muhammad Daniel Aiman bin Sinin with my metric number 230500739. So I will be talking about the third real-world application, which is cable tensions. So cable tension is a force that is transmitted through a cable, rope, or string when it is pulled tight by forces acting at either end. It acts along the length of the cable and pulls equally in both directions. It arises in response to an applied load. It doesn't exist unless there's something pulling on the cable. The cable transmits the force from one end to the other. So there are four characteristics of cable tensions. The first one is it always pulls. It can only resist forces that try to stretch or pull the cable. If a cable is subjected to a pushing force, it will simply go slack and cannot transmit that force. The second one is it acts along the cable. The direction of the force is always aligned with the axis of the cable, pointing away from the object it is attached to. It works to keep the cable taut and balanced under load. The third one is it follows the Newton's third law of motion. Every action has an equal and opposite reaction. If a cable pulls on an object with a force of 50 newtons, it pulls back on the cable with an equal force of 50 newtons in the opposite direction. The last one is it uniform throughout the cable. Cable is considered massless without friction or sagging. In such cases, the tension force is the same at every point along the cable. So this is an example for question for cable of tension calculation. There are two equations listed here. The first one is tension 1 sine angles of cable plus tension 2 sine angle of cable equals to weight. The second one is tension 1 cos angles of cable equals to tension 2 cos angles of cable. So as you can see in the image here, AD and BD are the tensions in the cables. 30 kilogram is the mass of the sign. 60 degree on both sides of point D is the angles of cable. So the object has a mass of 30 kilograms. So we need to find the weight of the object, which is equals to mass times gravitational acceleration. So 30 times 9.8 equals to 294 N. So the first step will be is to apply force equilibrium. Tension AD sine 60 degrees plus BD tension BD sine 60 degrees equals to 294. Since both angles are equal, mean AD equals to BD, it means that the tensions are the same. So we could start with 2T sine 60 degrees equals to 294, and it would end, and we will get the tension in both cable is 169.7 N. Static equilibrium is crucial in cable system. First, it ensures structural stability. Maintaining equilibrium prevents the structures from collapsing due to unbalanced forces. Every component remains in place because the forces acting on them cancel out. Other than that, safety allows engineers to determine the exact tension needed in each cable, which helps avoid overloading. If a cable is subjected to more tension than it can handle, it may snap, leading to dangerous or even fatal accidents. Third is design optimization. Knowing precisely how much tension is required, engineers can minimize the use of materials, reducing cost and weight without compromising safety or performance. Lastly is load distribution. Forces are spread evenly across all support cables. This is especially important in structures where the load is not centered, as an even distribution could cause tilting or instability. Real-life application that uses this cable system is suspension bridges. Suspension bridges use cables to support the deck's weight and transmit forces to the towers. Other than that, cranes rely on carefully balanced cable tensions so the boom can lift heavy loads before tilting or collapsing. Lastly, in zip lines, the tensions in the cable must be precise to ensure a smooth and safe ride for the users.
My name is Mohammad Haikal bin Partono, matrix number 2300638, and I'm going to be talking about real-world application number 4, boats and ship stability. When a boat floats on water, it is in static equilibrium when it is not moving up and down or it is not rotating. When boat floats, it is subjected to two vertical forces, which is the first, the weight of the boat and its contents acting downward towards the gravity, and also the buoyant force acting upward from the displacement of water. In order for both to be in static equilibrium, two conditions must be satisfied. The first, the net vertical force must be zero, and the net torque acting on the boat must also be zero, which is to ensure that the boat does not tip or rotate. This can be seen in real-world examples such as when loading cargo on a cargo ship, the weight must be distributed evenly to keep the boat balanced. This principle is critical for naval architects and marine engineers when designing ships, ferries, fishing boats, or even submarines.
Let's start off with why static equilibrium really matter. Static equilibrium is the reason bridges don't collapse, IV stand don't tip over, and boat don't sink. It's all core, it's all about balance, making sure the total force and torque acting on an object equals zero. We have seen this principle exist everywhere, from playground systems to complex itinerary like suspension bridges and crane. Engineers rely on equilibrium equation to calculate unknown values like force and tension, helping them design systems that are safe, stable, and functional. Understanding static equilibrium isn't just about solving that problem. It's a key to solving real world challenges, and as we've seen, good design isn't just creative, it's balanced.